I want to talk about two concepts today. The first one is something called an Atwood machine, and the second one is an elevator. I want to talk about how they relate to each other in relation to Newton's second law. First, I want to define these terms. Well, what is an Atwood machine? An Atwood machine is very simply a pulley. But the implication of an Atwood machine, or a pulley here, and you can see if I had a diagram like this, it would be a pulley attaching two objects. An Atwood machine is like a massless pulley. And the implication of that pulley being massless is that it has no effect on the acceleration. So we're not going to take it into account. Whereas obviously if that pulley did have mass and we had to use force to turn it, well, that would reduce the acceleration of the system. So right now we're going to talk about massless pulleys, and we're going to call those Atwood machines in physics, generally speaking. Let's take a look at a scenario here that involves an Atwood machine and see what the implications of it are. We have a scenario like this. A 5 kilogram object and a 10 kilogram object attached by a massless pulley. This is our massless pulley here. And we'll say if this surface is frictionless, and that's just for this particular scenario, frictionless surface, what is the acceleration of the 5 kilogram object? There's a couple of things I want us to note. First of all, Atwood machines change the direction of forces. Atwood machines change the direction of a force. So whereas before we had our Fx, our net force in the x-axis, and it was just all the horizontal forces acting on an object, and our Fy was all the vertical forces, well, it's going to be a little bit different here. We're going to see how an Atwood machine can make gravity act on the x-axis, for example. Let's draw a force diagram for this. Let's see all the forces that are acting on this situation. First of all, for that 5 kilogram object, we of course have a gravitational force downwards, and that'll be about 50 newtons, but it's counteracted by an equal and opposite upwards normal force of about 50 newtons. Let's look at what other forces are acting on this object. On this 10 kilogram object, we have a downwards force here, our gravitational force, and I'm going to call this 100 newtons as well, because it's 10 times 10 meters per second squared. What other forces are acting here? Well, we have a tension force pulling upwards on this object, and a tension force pulling outwards on this object. So we have those forces acting on these objects. If we look here, these tension forces, I'm going to tell you that right now, these tension forces are equal and opposite, whatever direction we define as negative. I am actually going to define this counterclockwise direction as negative, and that's typical in physics. I'm going to actually make that a note as well. Counterclockwise, I'm sorry, I messed that up. Clockwise is typically written as negative in physics. Clockwise is negative. Typically counterclockwise is positive. So anything that's in that clockwise direction, meaning goes in that clock direction, we're going to make negative here. So I'll make this negative 100, I'll make this negative Ft, and this is positive Ft because that's counterclockwise. So we have those forces acting on this object. Let's make some force equations here. Let's start with our forces on our y-axis. Well, our net force on our y-axis, let's look at the forces that are purely on the y-axis. We have this gravitational force, this normal force, and they are equal and opposite. I can make this one negative here, and we can say, okay, well, I have a gravitational force plus a negative normal force, and that equals 0 newtons on our y-axis. Great. And you might be asking yourself, well, why am I not including this gravitational force on our y-axis? And it's because, what does an Atwood machine do? It changes direction of a force. This gravitational force down here is now going to pull the block horizontally. You might see that in real life. If I set up a pulley system and I drop a block, it's going to pull down, it pulls the object across the table. So this object is going to be pulled across the table horizontally. So when I make my Fx, I want to include this gravitational force here. So let's set up an Fx equation here. And we have negative Fg plus Ft right here, plus negative Ft, which is this force right here. And we notice that those forces of tension cancel out. And that's always going to be the case. If we have two forces of tension like this acting on these objects, they are always equal and opposite. They will always cancel out. So our tension force cancels, and we're left with a total net force on the system here a total net force on the system, which is negative 100 newtons. It's just our Fx, because our Fy is canceled, our Fx was just Fg because the tension's canceled. So in this case, our Fg is negative 100 newtons. If I had a force of friction here, which I don't on this one, in that case, our net force would be that Fg, negative 100, minus this force of friction, whatever it is. But in this case, we're saying no force of friction, so don't worry about this. Right? We don't really have to worry about this for this particular problem. If our net force is negative 100 newtons, well, our question would be, what is the acceleration of the object? And we want to say to ourselves, well, that negative 100 newtons is accelerating both bodies. So we want to use the sum of our masses when we set up our next equation, which is F equals ma. So we'd say, okay, well, negative 100 newtons is equal to 15 kilograms times our acceleration. And you would divide that, and you would get an acceleration of 6.6 repeating meters per second squared. That would be the acceleration of both objects. That'd be the acceleration of both objects. They both would experience an acceleration of 6.6 repeating meters per second squared. We're using the total net force on the system, and we're using the mass of the system. In fact, I want to rewrite this equation more generally here. And we could say, well, once we find our net force, it's equal to m1 plus m2 times a. And what was our net force equal to here? Well, it was equal to Fg, which is equal to mg. And I'll write that as m1 times g. So we could really say here, well, m1g equals m1 plus m2 times a. Or our acceleration of the system is m1g over m1 plus m2. And this is the general form of this equation. Where is this coming from? Well, this m1g is our F net, which is equal to Fg for this object, because there is no friction. And this is our combined mass. So this is just F equals ma rearranged. Let's move on from this idea into the actual tensions on each individual rope. Let's take a look at what the actual tensions are on each of these ropes. Let's take a look here, and we'll say, okay, well, I want to know the force of tension here. We just found our acceleration on both of these objects, and our acceleration was 6.6 meters per second squared. Very interesting. Now, let's take a look at these tensions. We could pick either one of these to start with. It doesn't really matter to me. I am going to, in fact, start with this one because it's quite a bit more straightforward. I'm going to say, okay, well, what is that tension going to be? If we look here at this individual block, so now we're jumping from the system to the individual blocks. If we look at our 5 kilogram block here, our Y forces are balanced. This tension is the only unbalanced force experienced, which means that that tension is equal to our net force, which is equal to mass times acceleration. So the tension is equal to the mass, 5 kilograms, times 6.6 repeating meters per second squared. And we would calculate that, and we'd say, okay, well, our tension force here is 33.3 newtons. Great. What about this one here? What about our, and of course this would be negative. This should all be negative because this is clockwise. What about this one here? Well, what's that going to be? First of all, I told you these tensions are equal and opposite. So you already know that this is going to be 33.3 newtons. But let's prove it. Let's look at this block, this 10 kilogram block. And let's look at our two forces that are acting on this object. Well, let's say we don't know this one. So we can set up a net force equation. We say our net force here is gravitational force downwards plus our negative tension force. Or realistically, because we made that 100, that's going to be the negative one. All right, so we'll say negative Fg plus Ft. And we're saying, okay, well, the acceleration of this object is negative 6.6 meters per second squared. It is accelerating in this downwards direction. So we could say, okay, well, this net force equals negative Fg plus Ft is also equal to mass times acceleration. let's substitute in some values here and see how this works out. Well, you get that negative 100 newtons plus Ft is equal to our mass of 10 kilograms times an acceleration of negative 6.6 meters per second squared. You get negative 100 newtons plus Ft equals 66.6 repeating newtons. Negative 66.6 repeating newtons. We add 100 to the other side, and we get a tension force of, guess what? 33.3 newtons. Notice that while the first one was negative, this one is positive when you add 100 newtons to the other side. And that makes sense. Our tension force is 33.3 repeating. So, both tensions are the same. How could you find the tensions? You set up a Newton's second law equation based on the gravitational force down and the known acceleration. This, in fact, applies to all elevators. Let's take a look at a vertical elevator problem. So this is our horizontal elevator problem, and you want to realize here just some quick notes. Atwood machines can change directions. Your net force on an Atwood machine like this is going to be equal to Fg minus force of friction, although this one didn't have force of friction. And then you can find your acceleration by saying, well, acceleration is going to be whatever that net force was divided by the combined mass. That's if they are. Only one of them has gravitational force affecting it. This one had gravitational force counteracted by normal force. In a vertical Atwood machine, both of them are affected by gravity. So let's look at a vertical Atwood machine together. And if you look at our vertical Atwood machine, well, we have a pulley, we have the two objects that are hanging off of each side, and let's make up a scenario here. Let's say we have an 8 kilogram object on one side and a 4 kilogram object on the other side. And the first question is, well, what's going to happen to this system? And if you've ever seen a pulley in any form, you know this system is going to accelerate, and it's going to accelerate in this clockwise direction. Because this one's considerably heavier than the other one, it has a greater gravitational force acting on it because it has a greater mass acting on it. We also note that because Atwood machines change direction, these are pulling opposite on each other. So if we start drawing out our force diagrams here, well, let's take a look at what forces are acting on these two objects. We have a gravitational force downwards here, which is going to be equal to mg. So our gravitational force here is going to be negative 80 newtons. I made it negative because it is clockwise. Our gravitational force here would be mg, which is 40 newtons. So positive 40, negative 80. We also have a force of tension acting on these two objects. And we want to keep in mind that these forces of tension are equal and opposite to each other, but they're not equal and opposite to the 80 and the 40. Let's find the tension in these strings. What is our force of tension here? Well, first we want to say to ourselves, what is the net force on the system? These two tension forces balance out. So if we make a full net force equation here, we're going to have M1, I'll call these M1 and M2 just to make this easier. M1G plus M2G plus Ft minus Ft. And we see these cancel right away. M1G is negative 80 newtons. M2G is 40 newtons. So our net force here is going to be negative 40 newtons. That is our net force on the whole system. What could I find if I know the net force on the whole system? Well, I could find the acceleration of these objects. And we know they have the same acceleration. They're going to have the same acceleration as each other. Let's go ahead and find our acceleration on these objects. Well, we say to ourselves, I know F equals ma. And here we have the entire mass of the system. So we're going to have net force equals m1 plus m2 times a. So we get negative 40 newtons equals 12 kilograms times a. 12 being just simply adding these two values. And you work this out, I keep getting these repeating decimals, and you get 3.3 repeating meters per second squared as your acceleration. Now for this object, on the right side here, accelerating downwards, that is going to be a downwards, and that's going to be negative 3.3 meters per second squared. And this one will have an upwards, positive 3.3 meters per second squared. To find the tension, you could analyze either object, but we might notice that this is going to be accelerating downwards, the other one is accelerating upwards. Let's take a look here at what the tensions must be. You could choose either object to analyze this tension. I am going to choose this object, this 8 kilogram one here. We say to ourselves, okay, well, what's our tension going to be? Well, let's make a net force equation just for object 1. And we say, well, our net force is going to be our gravitational downwards here. We'll call that negative Fg. And then we have our tension force upwards. And I just realized I had these signs flipped. So I apologize for that. That's negative because it's clockwise. The other one's positive because it's counterclockwise. So negative Fg plus Ft. And that's also equal to mass times acceleration, by the way. Always equal to mass times acceleration because it's net force. So it's mass times acceleration. So all these are equal. Well, let's analyze this together. Negative Fg plus Ft. So we get negative 80 newtons plus an unknown Ft is equal to our 8 kilogram mass, because we're just analyzing the one object now, times our negative 3.3 meters per second squared acceleration. We work that out, 8 times 3.3 meters per second squared, we get 26.6 repeating. So we get negative 80 newtons plus Ft is going to be equal to 26.6 repeating newtons. We add that 80 to the other side, and we should get a tension force of 53.3 repeating newtons. Let's look at some other stuff going on here. So we have our tension here, 53.3 newtons, slowing the object down. It's upwards, it's slowing the object down. Does this fall with an acceleration of 9.81 meters per second squared? No, it falls with an acceleration of 3.3 meters per second squared, because this tension force is reducing it. It's preventing it from having free fall. As these get farther apart, if, for example, M1 is way bigger than M2, I'm calling this M1 and this M2. If M1 is way, way, way bigger than M2, the acceleration approaches 9.81 meters per second squared. As M1 and M2 become closer in value, the acceleration approaches 0 meters per second squared. If these two have the same mass, this system will not accelerate. And that brings us to our last concept related to this. And that concept is, well, what if I'm in an actual elevator? What if I want to figure out the values of a system where I'm in an elevator? And they could ask this a couple of ways. They could say, well, what's the tension in the string that's attached to the top of the elevator, the cable attached to the top of the elevator? Or they could say, well, what is the normal force applied by the floor upwards on the elevator? Or they could say, what would the scale read if you're in the elevator? But all these are different ways of saying, well, what is the tension force or normal force or scale force required to produce a certain acceleration? So let's look at some scenarios here with our elevator. Let's say, for example, let's say we have a 10 kilogram object in an elevator, and the elevator has an upwards acceleration of 2 meters per second squared. What is, let's say this is on a scale. Okay, so this is on a little scale here, 10 kilogram object. What is the reading on the scale? Which is another way of saying, what is the tension in this cable? Which is another way of saying, what is the normal force in the ground? Let's look here. We have an upward acceleration of 2 meters per second squared. 10 kilogram object. What is the reading on the scale? Let's analyze the system together. First of all, which forces are acting on this object? We have a gravitational force downwards, and our gravitational force downwards here, we'll say is negative 100 newtons. And we have an upwards normal force, or tension force, or whatever it is pulling upwards here, but we have a normal force here, and we don't know it. The normal force is going to be the reading on the scale. What we do know here is the net force. The net force, which is mass times acceleration. The net force here is 10 kilograms times positive 2 meters per second. Our acceleration is positive 2. So our net force here is 20 newtons. Let's make a net force equation involving these values. Our net force is going to be, well, it's 20 newtons, which is equal to our gravitational force plus our normal force. That means 20 newtons equals negative 100 newtons plus normal force, and our normal force here is 120 newtons. Notice that this upwards force has to be great enough to not only overcome gravity, not only come a downwards acceleration of 10 meters per second squared, call it negative 10 if we want, but also produce the 2. So it's like our acceleration here was 12 meters per second squared. And that gives us our generic normal force slash tension force slash scale reading equation for elevators. And that generic equation here is going to be our normal force on an elevator, or our scale, or our tension force on an elevator, is going to be equal to the mass of the object times g plus a, taking sign into account. Taking the sign into account. So in this situation, well, what was our normal force? It was m times g, 10 meters per second squared, plus 2 meters per second squared. And our m, of course, was that 10 kilogram mass. And this should give us 120 newton force upwards on that object. And that's how much force is required to bring this object upwards. Some scenarios here, and these scenarios are written on slides 59 to 60 of the forces slideshow. I'm not going to go through all the scenarios, but basically, you take this object. If it's speeding up upwards, you're going to add these. So if acceleration is upwards, you're going to add these. Two ways acceleration could be upwards. If it's speeding up upwards or slowing down downwards. Both of those are positive acceleration, upwards acceleration. You're going to use that m times g plus a. That's if acceleration is up. If acceleration is down, which means the object is either speeding up downwards or slowing down upwards, it's m times g minus a. If the elevator is in free fall, meaning it's just dropping freely, there is no upward tension force, this is like the cable snapped, well then our normal force, or our tension force, is 0 newtons. This scale is not supporting anything. It's also in free fall. And if you're at a constant velocity, well, our value here for this scale is simply mg. All forces are balanced. It's in a state of equilibrium. So that would have an equal and opposite normal force, or tension force, and gravitational force downwards. This is a considerable amount of information. That's everything about Atwood machines and elevators that you need to know. The big takeaway, if you've learned nothing else from this, is set up net force equations, set them up on x and y values, and make sure that your net force equation agrees with your force diagram and produces the accelerations or whatever other values that you're given. We have plenty of practice with this.